All right, so let me know if the screen is coming up now. It should be. Is it visible?
Yeah, this
Yes, sir. Visible.
Okay, nice. So week three we ended with data flow, and week five also we discussed like logic basics, initial part at least. Okay, coverage criteria and all. Maybe we can discuss a little bit in this session if the time permits. But the idea is not to go into detail with this one because we continue in the regular session itself. Okay, this is more like just to clarify the doubts and things like that. Whatever has been left out. Okay. So, so a little bit of week four first, and then we'll move on to strongly connected components. That was a request from one of you to discuss that. Okay, so essentially we discussed about unit testing. In that, what happens is you are testing the modules individually. So think of it like a team because these things also there's a little bit of overlap with engineering also, software engineering. So it is good to think of in terms of teams that are working on a software application or a program. Okay, now it rarely happens that software is one module, like as in we call it a monolith, but there are different meanings of the word monolith here. Okay, even a monolith might have different modules, but that's a different discussion altogether. The idea is that it's not going to be a singular thing essentially, right? So what we do is we divide component wise or module wise. That's why I call it modular. That's a good thing, right? It is a positive thing that the software is modular. In that, it allows for modifications and extensions easier later on and upgrades, right? And updates to the software is something inevitable, right? It is bound to happen. We cannot avoid updates unless something becomes obsolete in the long run. That's a different thing. But if you're going to have something in the market, you have a product, then not having updates is not a choice, right? So there has to be updates, and if there has to be updates, then engineering also plays a very crucial role. Okay, even with the advent of AI tools, uh, what we say, and this has been the sentiment in general, that engineering is here to stay, and that's what sets you apart. Okay, so nonetheless, that's a different discussion. Idea here is that so since we are dividing to different modules, uh, so unit testing is one part, right? So you are working. So let's say a developer is working. I am working on a particular piece of code, a particular module. Someone else is developing something else. So they themselves, being developers, they themselves test for the working of their module. So that's what we call unit testing. Now the term here unit also differs from context to context. It depends on how the team has defined it. And now even within the team also it varies a little bit, right? So this unit it may be a class for you, it may as well be a method for you, or it may be a module, or it may be something larger than that, right? So what is unit generally differs depending on the context, but you can assume it to be a class or something less than that, for example, just to proceed ahead with the discussion. So what I'm saying is that I am working on some module or unit, and another person is working on some other module or unit. So they are going to do unit testing for their own module, right? Now when the time comes to integrate it, meaning see one part is going to be somehow dependent on the other part, then that's how they work in coherence, right? There has to be some call that goes right back and forth. So let's say easiest example is you have a class A, class B. Now some method is there, so class A is calling class B, and vice versa. Maybe class B is calling class A. So whoever calls is known as the caller. So class A is calling something in class B, and that is not even within your own program. It might be something outside also. Let's say libraries, right? So there are various libraries that people depend on. Okay, so when you call something from the library, you're calling external thing, right? I mean, different module, that is. Okay, so that's what it is. So integration testing within your own software, apart from libraries, even your own software is divided into different modules, and unit apart from unit testing, you have to do integration testing. Okay, also. So that's what we are going to discuss in this particular week: software design and integration testing. How do we do that? Okay. So this one we've discussed the graph coverage criteria. We'll come to that and see if we can connect the dots at certain places. That's a different thing. So idea is that yeah. So in a nutshell, that's what I described. Software design basically dictates how software is organized into modules. Modular component is a self-contained element of a system, and this idea one needs to be clear about. I mean, this is like self-explanatory, but still, just have to remember this. Now, what happens is when you are going to talk or interact with other modules, there has to be some sort of a well-defined interface. So think of interface like a plug, right? So for example, in electronic equipments, there's a so for in India you have this circular plugs essentially. I mean, you get the idea what I'm trying to say, right? So and then you have these sockets which are accepting those three pins essentially, so that goes in. So that is what an interface is, right? So we all understand that if the plug is of that kind, so you go into the market, get an adapter for your phone or laptop or charger, right? So that is having a plug, a specific kind of plug. So that's the interface, right? So that gets plugged into the socket. So it has to be, what has to be compatible, like the socket has to be compatible with the plug and vice versa, then only the plug can get in. So that is what the interface is precisely. That's what we're taking it, that's where we're taking it from, right? Interface. So even in between your modules, there is a well defined mechanism of talking or communicating with each other, meaning in the modules, between the modules, and that is what is known as interface. Okay, so it says interfaces implement a mechanism for passing control and data, both control and data. We'll come to this aspect a little bit. Why are we differentiating between control and data? This is something to keep in the back of your mind for now. Just a second.
Is it like API?
Sort of like API, yeah. But we are talking, so yeah, of course an API, of course. But even the term API differs, depending on the context in which you're talking about. Like there are different sorts of APIs, but you are correct. Application programming interface is what it is. Okay.
Yeah, I'm thinking like the API and SQL or like library which is well defined.
Hmm.
Yeah,
Methods and parameters
yeah,
it accepts, so you
yeah,
give it. Yeah. So for example, any machine learning library, for example, I'm just making it up. So any machine learning library might have interfaces having train and test methods in it, right? So train and
yeah.
then test and things like that, whatever it may be, right? So they want to stick to a particular kind of interface because people are familiar with that. That is one aspect. But there are other aspects in interface design also, like because in large software, think of ERP systems or operating systems for that matter, right? ERP systems, operating systems, or your web browsers for that matter, right? Very huge code bases. In that, these decisions are having important consequences. Okay, so it is not like, so that's what software design is about. Not only about interfaces, there are other intricacies involved in system design, low level design, high level design, and things like that, right? And if you expand
Okay.
it to when you expand it to cloud, then other things come into the picture, right? Network, latency, CDN, redundancy, replication, and things like that.
Yeah.
Lots, yeah. So all this jargon is coming from this only. So this is like the bare minimum, and from here we extend. Okay. So go ahead, Indal, if there is any question, please.
No, 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 no. No.
Okay, thanks for that. So integration then says begins after unit testing, which already I explained hopefully, and you understood what I mean. So apart from the unit that they are doing, meaning the developers are doing, which what I am doing, what the other developer is doing, once they do it, then they push it essentially, push it to a Git repository, and then there is a continuous integration process also, CI, and there's also a related process called CD, the CI/CD pipelines. You might have heard of that, and some of these things you're going to see in software engineering hopefully as well. But idea in continuous integration is just that. So what they do is, once someone pushes to the Git repository, right, there's a CI server which takes care of automatically running that integration tests. You see, so think about it this way: I had three or four modules, all of them were working, so my tests were passing. Okay, like the software was okay. Now somebody decided to do some change in their module for some reason, maybe some payment module is there or something, email module, payment module, thing like that. Right. So maybe I decided to do something with the authentication module, for example. Now suddenly some bug got introduced in that, so integration will fail, right? I mean, because not everything is working properly. So as soon as you push it, ideally they don't push it unless they test locally. But assuming that for some reason some small bug came in, that is only there in integration. So it might be that individually the modules are working. That's what I'm trying to highlight here. So maybe your unit tests are passing. So you are satisfied that okay, whatever change I have made, it is going to work. There's no problem in that. So it's fine. Now I'm going to push it. Okay, once you push it, then comes the integration part. Maybe it is not okay with other modules. Maybe you change something with respect to the interface which the other module is not expecting. You wanted some extra parameters. So that other module is not passing you that. No, so some null exception is coming, null pointer exception is coming, because that something could happen, right? At the time of integration, when they start talking to each other essentially. Okay. Because unit is one part, but everything is working together is another story. Okay. So that's what it is. So each module. So once it is done, then we are going to do integration, and there are several approaches to that. Not several. I mean, a couple or so we've discussed in this particular slide deck. But yeah, I mean, there are other things involved in that also. If we extrapolate, but in general, few processes we have described, like the Big Bang. Not the Big Bang. Big Bang is not even incremental. But in incremental, you have top down, bottom up, sandwich, and other kinds of ways we do that, right? Anyway, so that's what it is. Integrate into a bigger working component. That's the idea. So see, what could go wrong? My units are working, no? That's what it is saying. Each module has been unit testing. So it means clearly that everything was working individually correctly. Everything was okay. So what could go wrong then? The thing that could go wrong is communication, right? I mean, that's what it is. Communication between different modules. Because if individually in isolation something is working correctly, and module A is working, module B also is in isolation working correctly, and with then only when I integrate them together, they are not able to communicate well. Maybe the stubs were working. So remember stubs that we discussed in the previous class, test stubs. So on the stubs it was okay, but when I integrated with the real thing, it started failing. So what could go wrong? Interface only, some communication issue essentially. That's what it is. So therefore, the focus in integration testing is to test the interfaces and the communication aspect of it. So control and data between modules. That's what we're going to test. Okay. Module after module. That's okay. And yeah, there is another aspect to it, software hardware integration also. But however, this is not within the purview of our discussion and course in general, but it is good to keep in mind that there is also a concept of software hardware integration. Right, because I talked about two modules communicating to each other within the software aspect itself. Right, but it might be that you are running something on the emulator or simulator. I mean, emulator might be a good word to use. Okay, and on the emulator, perhaps it was working correctly, but then you put the actual software on the hardware. Some sort of robotics system or something like that. No, or maybe smart. Uh, what do you call it? Elevators or other such things, right? I mean, which involves some embedded systems essentially, right? Your elevators are smart also in some sense. Waiting time and all, they optimize for certain things. There's an elevator algorithm. For those of you curious about it, may go and uh, check that out. That is more complex than it seems on the surface. Okay, like how to optimize and what to optimize. There are trade-offs only in that. When the elevator goes into which floor, how much waiting it does, and so on and so forth. Okay. Anyway, that's a nice one. So that's what the idea is, right? When you put that in the actual thing, maybe because once hardware comes into the picture, there are other whole lot of other issues that may come in, and it may cause software hardware integration issue as well. But anyway, we are not going to discuss this one. Software is what we are focused on. So with respect to communication, there are few well-defined ideas. Okay, and some of you might be able to relate to it also. Okay, few three things I think we have described here. One is procedure call interface or method. So procedure is like a method. Think about it like a method. So procedure call interface is a procedure method in one module calls. Call is an important word here. Calls a procedure method in another module. Simple enough, right? Within the same program, within the possibly in the same source code, you're calling from one thing to the other thing. Okay. So you're passing control and data. Why we are saying control? Because you remember if I am calling. So think about it this way: class A, I had something. Now I'm calling class B. So what happens? The machine, the virtual machine, the JVM or the interpreter in case of Python, the control itself shifts there. No, the line of code that is being executed by the computer is there now. So it is looking there. No, and then unless the method returns back, it doesn't come back. The control doesn't come back to right. So it is like think about it like in the control flow graph. What happens? So you are doing something and then you call something external. So it goes away. The control goes away and executes that thing. What is there in the other method, and then comes back and it continues execution. Right. That's what happens. So it is not. It's like jumping somewhere else. So that's why it is control. That's why we are saying control could be passed also in this case. Procedure call interface. Now before coming to shared memory, I'll come to this message passing interface. Now, not to get confused. However, there is also a remote procedure call. So this was a procedure call interface. So the one that we are discussing here is within the same program, within the same process to be precise. Okay, and there's a concept of inter-process communication, IPC, and things like that. If you, for those of you interested, might look into that. But this is the most general definition of it. I mean, in the same program, you're calling something, just like method or within a library, or like you are within the same what do you call program in some sense, no? And excuse me. Another variation of this is remote procedure call. So that's what RPC is. Okay, RPC, remote procedure call. So remote procedure call, it behaves as if it is a procedure call, but it happens remotely, which is like message passing. Okay, so RPC is not message passing in that it passes control also. Okay, but it is not procedure call also because it is remote. So it is as if you are working on the same machine, but you are calling from somewhere else. Okay, or some other process even on the same machine there are different processes that are communicating with one another, right? So that might behave like a procedure call. On the outside it might appear as if it is a normal local procedure call, that is, but it might as well be a remote procedure call, but it is at the end of the day procedure call. So all the aspects of procedure call will be applicable here, but that is not what we have discussed here. I've just mentioned that remote part that we have not discussed, but there is also one thing called RPC. Okay, now message passing is the purely message passing interface that is completely decoupled. There is no coupling here. So think about web sites and web applications, right? What happens is a client web browser calls something, meaning requests, sends a request. So HTTP request goes to google.com. It returns me a web page, and that's what the browser downloads. So there is no direct coupling between the server and the client. I mean, the message goes through, and accordingly it responds, right? But on the program side, there is no like there is no overlap as such. That's what message passing is, right? One module prepares a message of particular type, sends it to another module through this interface. So client server systems, your email client, no? So Outlook. So Outlook is like an email client. It downloads emails from servers, right? So that's like a client server system. There is no one program resides somewhere else, the other program is somewhere else entirely, and they are communicating through messages, right? Essentially, so that's what your REST APIs and SOAP APIs are. Okay, so even RPC is like message passing, but that behaves like a procedure call. Okay, and normal procedure call is, you understand what it is, right? Just like calling, no? So B dot A or whatever, that kind of thing. Now, shared memory interface is like a block of memory shared between two modules. So it is like global variable. The easiest way to think about it is like a global variable. Some fixed memory block is there, and two things are reading writing from the same place. Okay, so that becomes a shared memory interface. Okay, so data is written to and read from the memory block by modules, and the memory block can be created by a third thing also. So there are three modules, let's say. The third module creates a memory block like a storage space, right? And that same data is being read from and written to by two other modules to the same memory block. Okay, so that's shared memory. I mean, you get the idea, right? What happens? Like I fixed a space wherein I am going to read and write from, essentially. So this is not like message passing. Rather, I'm just directly reading from where the other thing is stored. So global variables are like that. For example, in global variables, you declare it once, and then two different classes are accessing the same piece of information, essentially, right? In any questions on this? Important to remember the definitions, though. Okay, there might be questions on this. Okay, so I'm assuming it's fine. Now, there's some empirical studies of it says that up to a quarter of all errors in the system can be interface. Of course, because see, individually one thing might work, but it is only when you integrate problems start to arise, right? I mean, end-to-end testing, then only you get to see the errors. So 25% or so is coming from there. Anyway, these things could be there, right? Uh, some categories. I'm not going to discuss that in detail, but you get the idea, right? Most of the errors are coming because of the communication problem. Okay, so to do integration testing, yeah, that's what the key part is, right? Now I am working on a module, but I am supposed to call something also, maybe another class, but that other thing is still in work in progress. So that thing is not with me. That other thing that I'm going to potentially call later on. So what do I do? Do I wait for the other thing to finish and then only proceed? Maybe, yeah, maybe there are certain things which are ready, certain things which are not ready. So I cannot wait for all the dependencies to fulfill and then only proceed with testing. So what we do is we use scaffolding. Okay. Scaffolding, there are two common types of scaffolding. One is test stub and another is test driver. So I'll go to the graph, meaning there's some diagram there with which I'll explain it. Okay. So it says, and remember the definitions also. It says test stub is a skeletal or special purpose implementation of a software module. It says a skeletal, right? Skeletal is the keyword here. It is just an skeleton. It's not an actual thing. It's a stub. It is as if it have the interface. See, what does it mean by skeletal? Skeletal is the interface is the actual interface. Okay, but on the the implementation is not actual. So implementation is dummy, but interface is actual. That's what stub is. In the actual module, you will have the actual implementation and the actual interface. So the other thing calls, you are able to do the thing and then return back whatever value is required, right? Think about like a calculator. So in the add method, I should have a plus b, right? So in a stub, it will just return zero, for example, but it's still returning. No, add method is there. I'm calling the add method, but it is not actually adding it, rather returning a fixed value, a dummy value from it. So the implementation is not there, but the interface is there. That's what skeletal means. Yeah, that's what test stubs are meant for. Okay, so that at least the other thing which is ready can still call it as if it is an actual thing, actual module, but the other module is still in work in progress. So we are using stub in place of that. Okay, so stub is callee, meaning that which is called from something else. So stub is never ready. It's not the complete thing. It is dummy. So this dummy thing is being called from something which is ready. Of course, some module is ready. I'm going to use stub to. I mean, basically, I'm calling the stub just to act like a bridge, essentially. Okay, so that I could test the other things. Whereas test driver is what sits on top. So I'll show the graph also. This is the caller. Okay, so it depends on which approach you're using. There are four approaches. I'll think. So test driver, remember this is caller. This calls. Okay, and stub is the thing that is being called. Okay, and I'll describe the differences between the two also. See, there are four approaches here, essentially. I mean, in incremental, these four. So of course, top down, bottom up are incremental approaches, and there is sandwich also, and then big bang. Big bang is once you do the entire thing, then you test. So there is no integration. I mean, there is no incremental testing there. So the name suggests big bang. It says after everything is done, then only I'm going to test. Now, if you do that, then you don't know what will fail, and if something fails, you don't know what is failing. I mean, where to fix, what is the root cause, because everything you're testing at once, so you don't know, right? So better to do on incremental only always, and there are three variants to it. See, this is the situation. So call goes from top to down always. Okay, so A is calling B, C, D. A is dependent on B, C, D. If B, C, D are not there, A cannot work because A is going to call them. No, so B, C, D, and C is then dependent on E, E, F, G because C is calling E, C is calling F, C is calling G. Something in G, some method in G. Now this is the situation. Okay, white ones are actual modules, meaning the ones which are ready. So I'm building from top down. Top down integration says it depends on how the software is being built also, or a portion thereof. Okay, I mean for a large software it could be a mix of both, therefore sandwich, but I'm talking only about top down for now. So top down, the above thing is ready, so the thing that is going to call is ready, caller is ready, right? Now, so A is ready, B is ready, but A depends on C and D, so I want to test integration between A and B. Okay, my purpose of integration testing at this point, step one, is to test integration between A and B. But just because of the fact that C and D are also there, on which A is dependent, right? I cannot stop and wait for C and D to get finished, only to test between A and B, the integration. So what we do is we, instead of waiting for C and D to finish, we use stubs. Okay, and let us do testing for A and B at least, and C and D can be stubs. That is the idea. So therefore, I said stubs are always below and they are being called from the top. Stubs are callees, essentially callee modules. Now, so similarly, D gets ready. Now D is ready. D is the actual module. Now I'm testing between AB and AD. C is still not ready, so I'm using stub there. Now once A, B, C, D is done, so I'm testing integration between AB, AC, and AD. Okay, but C depends on certain things which are not ready, E, F, G. So I'm using stubs in place of that. This is top down because I'm building from the top. Call always goes from top to bottom. Is that okay? Any questions on this?
No.
Good. Okay, so we are going to
No,
go
sir.
forward. Thank you. Now, similarly, so once we finish EFG, now E gets ready. So what I am testing integration on? A, B, C, D, E. Okay, is the actual thing. So I'm testing integration. Let us test. Meanwhile, F and G are getting ready. So what to do? Because what will happen if I don't use a stub? See, if I don't use a stub, then C will throw error. No, C will say that okay, I'm trying to look for F. F is not there. What should I do? I'm looking for G. G is not there. What should I do? So I have to have something like a placeholder for the time being. So that's what you're using ISTA module. So therefore I can do the other things at least. A, B, C, D, E. F, G are getting ready. Now F gets ready, G gets ready. Finally everything gets ready. So I'm then doing complete integration testing. So this is the incremental approach. And incremental approach, be it bottom up or top down will require either test up or test drivers. Okay, and even if you're doing sandwich is most likely what you're going to see in real world because you do both. Now, excuse me. Bottom up is system integration begins with the integration of the lowest level modules. Okay, lowest level module is the one that does not invoke another, meaning it does not call. These are callees. Okay, meaning EFG are not calling, no. E is not calling anything. F is not, like, this is at the base level. F is not calling anything. G is not calling anything. So these are not callers, rather callee modules, right? So integration could also be from the bottom up, and that's what we are discussing here. Okay. So in this case, situation is different. See, I'm starting from the bottom. EFG get ready first. Okay. So what to do? I mean, I don't have the thing to call them yet because A is supposed to call, but A itself is not there. The caller is not there. So I use a test driver. Therefore, I said test driver is caller, test stub is callee. Okay. So I make a EFG first, and then so test driver acts like something which will call. It is not skeletal. Okay. Test driver is behaving like the actual A, not like actual A. You get the idea. I mean, it's basically the purpose of that is to test the interfaces only. So it calls with certain values. Might not be the actual values as what A would give or BCD would give. Okay, but it just calls them, right? It will call E as if A is calling that. It will call F also, G also. Therefore, I could test these three, and then so I go to the other level now, bottom up, right? Now BCD are ready, but A is not. Excuse me. A is not ready, so I need something. So I'm using test driver. Once A gets ready. Now we are at the same place as the final stage in top down or bottom up. Because at the end, if everything is ready, then both outcomes are same. Okay. Now sandwich.
Hello.
Yes, Indal, please.
Yeah, I have just one doubt.
Hmm.
Actually, as per I thinking, like
Hmm.
where we use bottom up, right? Because as per I thinking,
Hmm.
the main function are tested later, right? So we are moving from bottom to up.
Hmm.
So if the main function are calling at the top
Hmm.
and the main function calling other
Hmm.
function, so we are testing the main functions later.
Yeah.
Is this so? So the thing is like when we use bottom up, like
Yeah, I get your point. What you're saying. You're saying like, why is it that because see, if the first thing is not ready, then how is it that we are starting from the bottom, right? I mean, this is supposed to call
yeah,
this like the
exactly.
main thing. So if it is not there, then how are we testing this, right? So see, idea of the test driver is to be able to test in between also. No, for example, B, C, D are callers. No, I get your point. Like if I have just the test driver, then it doesn't make sense. I mean, there is step one, there is no integration per se because.
Exactly.
Hmm, I mean, step one, we don't have integration because there are no multiple layers, right? So it's just calling the base module. I mean, in some sense, it could be because still you are testing the interface for EFG, right? EF and G. But this is more reasonable, right? Here,
Yeah.
even the main module is not ready, as you're calling, right? Main module is not ready, but at least we are able to test between CE, CF, CG. We have to test that, right?
Mhm.
So
Exactly.
we need something to call it because C never supposed to call. If C were the caller, the actual main as you're calling, then it would have been on top. I mean, for this portion of the graph, C, E, F, G, right? This portion C is like A only, no? I mean, what A is for the whole thing, C is that for the below portion, no? The subgraph.
Yeah, I understand. I
Yeah,
understand.
exactly. So I'm testing C, E, F, G at least, but I need something on the top also, like the main thing. So unless I have the
Ah,
main thing ready, I'm testing with respect to this. Okay.
yeah, thank
And
you.
test drivers is like it is used. So for example, uh, I mean, it could be a different context also. Think about it this way: it might not always be for testing. See, if the program is there, then somebody is going to use it, right? So don't think like testing for now. I mean, of course, this is integration testing, but another dimension that I just wanted to highlight, maybe it'll allow you to connect the dot. See, even if you're not talking about testing, assume everything is ready, then somebody from the top is going to call it, no? I mean, some user. So even if A is ready, I am going to use it. Like I begin
Yeah.
from here. Like this is the main method, so I begin from here. Right now, test drivers, they can also be used to automate a program, and the most famous use case is with browsers, web browser automation. They use test drivers only. Okay, so because What I could do is I could call the web browser as if somebody is using that. Okay, so it will like interact with the browser, right? And I can do web application testing through that. Okay, so this could also be for automation, not necessarily for testing, but yeah, it helps in integration testing also. Test driver. Okay.
Okay.
So and sandwiches. So sandwiches, think of a very big graph. So this is like a small graph. Now you just make it very big. Lots of other modules, some modules and things like that. Now at some places, some small portion of the graph, maybe you are doing top down, and some other in the same graph in the same large program. Some for some other, some portion of the program you are doing bottom up. So some things you are integrating from top to, because for some time, rather for some layers, some modules are being built from bottom, and from some other parts are being built from top, right? So that will become sandwich, like, because I'm doing both sides integration essentially. Okay, so that will require use of what? That will require use of both test drivers and test stubs. The places where you don't have the caller available, on that place you're going to use a test driver. The places where you don't have the callee available, there you will use the test stub. Is that okay? So that is sandwich essentially. Okay, and big bang is like, big bang there is no incremental testing. Once you like, we are getting to step 3 directly, and then testing. No, so here, now here, if something fails, think about a large system. If something fails, we don't know what caused what issue, right? And then analysis or isolation of fault is also difficult, no? Because unless you isolate what is causing what, it is difficult. But here, what will happen in test driver? The test driver is calling it. Assume this integration fails, then I immediately know it is with respect to EFG only. And even more so, I might be able to figure out that this is with respect to E only, right? So I might be able to fix it immediately without waiting for B, C, D to get ready. Now, when C comes in the picture, when C interacts with E, this is corrected already beforehand. Okay, and easier to fix also because you have less things to worry about. Okay, that's why we do incremental. So Big Bang is discouraged actually. We don't do it. Okay. We virtually never do it essentially. Okay. Yeah. So there, excuse me. There is some discussion about calls over interfaces. So you just have to understand the first definition, last use aspect. Okay, so there's some rule to it. It's fine. I'll just skim through it because that's not important as such for the time being. Okay, so I just skim through that. So similar to how you had control flow graph, you have call graphs also. Okay, like what is calling what, and nodes could be then modules, actual modules, or it could be test stubs, or it could be drivers, and edges are interfaces. You understand? Like how the call is being made. So call graph looks something like this. So this is a different module. I have a small CFG for that. This is on the left hand side. I have another module. Now B of X is calling this. So there's some, think of it like public void B, some declaration, and it is doing something, no? Printing. So B is calling. Now this is another module, this box. So now B of X calling B of Y. This is edge that you're seeing between B of X and B of Y. B of X points to B of Y. It says this is a call to another module. So think of the left module as module A, right module as module B. So module A is calling module B. This is a call interface. Okay, so this is what we test, the edge. Okay, so this is what it is. Caller is your driver or module. It calls, and B of X is the actual module. Okay, rather sorry, is the actual parameter that is being passed in this method. This is the call site. Okay, this is the call site, meaning the call where the call appears. Because when I invoke that method, no, B of X, then it gets called, right? So this is the actual parameter. Now it goes. So here's the interface, right? So this is some other place. This below method is some other place where I have defined it. So this is known as the formal parameter, because remember, actual parameter is what you pass at the time of calling. No, formal parameter is what is being used in the declaration. So you have def of, let's say def is even, right? And you take a number int n there. But at the time of calling, you might pass some number or some other variable. So the name will change, right? Maybe they're the same name, but the name might change, right? So here we call it the formal parameter. Here we call it the actual parameter. At the site of when we are calling, when at the location of the call, it is actual parameter that is being passed, and in the declaration it is formal parameter, right? So X here will come as Y here in the other method, right? Because the declaration is like that. So this is b of y. So I'm checking z equal to y. I'm checking something and then accordingly proceeding forward t equal to y something and then going forward, right? So here I've called with x. The value that was taken is that of x, but here it is known as y. So the name only changes. But this idea we are familiar with that already, no? Because the name of the variable may change depending on where we are calling it essentially. Okay, so this is the actual parameter, this is formal parameter, and this is the callee, the called module. Caller is the caller, the one that is. So a module that invokes or calls another module. Callee is the module that is being called. It's like a receiver, for example. Okay, actual parameter is variable in the caller. Formal is variable in the callee. Call site is this, where the call is being made. Okay, so there's some sort of coupling. This part is important, at least this much you can remember, because maybe we're not going to data flow that much, but this is important. Okay, so parameter coupling happens. Types of coupling. No, how what is coupling? How two modules are linked together. That is what coupling is. Okay, so parameter coupling is parameters are being passed in calls. So the coupling, the way two things are being coupled is through parameters, right? Meaning here I am passing x, right? And here it is y. So the common thing in some sense, no, the overlap between b of x, the call, and here the declaration b of y, the common thing that is there is the parameter that is being passed. No, so the coupling, the nature of coupling here is parameter. It is the parameter being common between those two. You see, the link in some sense becomes the parameter, what I am passing there. Okay, so that's why it is being coupled through parameters, right? Because that's the shared thing essentially. The parameter in the caller is the same as the parameter in the callee because that's what I'm passing, no? Passing it. So in the other method, I'll get the same thing. Okay, so that's why it is coupled. Shared data coupling is two units access the same data through global or shared variable. This is similar to shared memory coupling. So sorry, what was that? Uh, Shared memory interface. If you are using shared memory interface, then shared memory coupling will happen. Okay, because there's some global variable you are using. Two things are accessing the same thing. So the nature of coupling there is shared data through shared data. Okay, external device coupling happens when two unit access an external object like a file. So you have a common file on the hard disk or the ssd, right? And two different modules are calling the same thing. Maybe some settings file or something is there, some config you're reading from it, no? So, and maybe two modules are reading the same file. So the coupling, the nature of coupling that happens is through that. Maybe the modules themselves are not related internally in any other way, but only because they are calling or referring to the same thing outside, and that's why they are coupled. Parameter coupling, yeah, I've already mentioned why, and similarly for shared data coupling also. It might be that the modules are completely in isolation otherwise, just that they are shared. The variables are shared. The global variables are common. So therefore, so coupling happens because of some common object that is there. Okay. Message passing interfaces, there is no coupling at all, like the least amount of coupling. I mean, there is no coupling, right? This is like completely decoupled. Like for example, you just send a signal or a message, and the other party essentially receives it and then processes it for you, right? So there is no coupling as such, right? I mean, the least amount of coupling. The only thing you have is the interface, your REST API or your what do you call the SOAP API or REST API that is there, right? Or even for RPC calls, remote procedure calls, the thing that goes through is the message. So your payload is the only thing that is shared, right? So there is some contract meaning some kind of interface that is fixed. Like for example, if I am calling API upload, right? So the upload API accepts a file, a PDF file to upload, right? So I know the format, I know what needs to go. I need to give a file name in JSON. The JSON goes or XML goes. So that is what message passing is, the artifact, the payload essentially, right? So that is so there is no coupling because those two things are completely different systems. It might be different systems also, no? And then they are sending receiving messages. So web systems are very popular. That's what they are. Your REST APIs are message passing interfaces basically, because there's no parameter, no shared data, no external device, only messages. So least amount of coupling here. Okay, so what happens is this. I'm not going to in the detail of this. Basically, what happens is we're going to discuss last definition before the call, of course, because what goes in the other method, the thing that is the last value of, so x is being redefined multiple times, no? X is equal to 1, x is equal to 2, x is equal to 3, x is equal to 4, b of x. So b of x, when the call is being made at the call site, the last definition will be taken. So 4 will go. The last definition was 4. So I called b of x, so 4 will go, no? So we consider the last definition and first uses inside the module to consider the interprocedural due pairs. Interprocedural mean between two different methods or modules, essentially, no? So how do we then couple? Remember, due pairs, what you used to do? A definition at node number so and so, use at node number so and so. But here, in this case, we are going to a different CFG altogether, or some other module, right? So we are going to consider the last definition as the definition, of course, because that is what is going to go finally, no? And the first use inside the other module after call, meaning in the b, so b of x, so in the other module we are going to just take the first use. Okay, that's how we construct the interpositional due pairs. And this is just definition, I think. We just go through that, it'll be enough. We are not going to go to too much detail as of now, at least in this one. It's fine. uh, okay, so first use is a set of node that have use a variable y and for which there is a def clear path. Again, same thing, def clear path also we have to use, and there's a concept of use clear path. Essentially when you are coupling, no, then in between there should not be any definition again on use, so like this. So this is the last definition. Above that there might be other definitions also. Just before the call is made, I have this definition, x is equal to 14. So this becomes my call side. So here what will go, we understand from programming that 14 will go here because this is the last def. So again, the due pair is constructed like this. So x is equal to 14 and print of a, this is the first. So why? Because remember, this is the actual parameter, y is being y is going here, it is g of a, so here rather, sorry, this was print here, g of x is going, no, so actual parameter is x, here it is known as a, so formal parameter is a, so x is holding the value of a only, rather a is holding the value of x only, no, because that's what I passed. What I passed is going to come here, right? So print of a is actually print of x, right? So this is the first use. Immediately after coming inside, I'm printing it. So I consider due pair like this. This is the definition. This is the use. Last def, first use in the other thing. So this is the column module, the calling module. Okay. Similarly, when we are returning back, when we are, so because remember return is also there, no, return. So we, again it's like a call again, call back essentially. If we want to go back, the control is going to, from after this method's ends, we are going to continue, right? So we'll come back from that. So return b, what happens is this is the first use for the other one. Now this is the last def for b here because we are returning b, no? So this is the last def for b here in the callee. When I'm returning back, this becomes the first use after coming back from that. So after the call side, I'm inside here. Control gets shifted to callee. Now I'm doing print of a, then so and so, and then b equal to 42, and then I return. So once I return, I come back here. Y equal to 42 now, right? And then I'm doing print of y. So this is the first use. So similar to how I did last def first use here, in the, so there has to be two ways essentially. Once you return back also, this is the last def here and first use here. Okay, that's how you couple it. This is the coupling DO bits. Is that okay? Any questions on this? Understandable, right? Hopefully. Any questions?
Yes.
Okay, fine. And then, okay, so yeah, essentially that's what happens. So again, we are doing it. So last definition set 2 and 3, of course, because yeah, here it depends. See, this is like a conditional, no? At 2, it's a conditional, like a if a statement. If it might be the conditions are not given because that's not of concern at the moment. What we are saying is if x is equal to 4, then b of x could happen. So what would be the last definition in that case? If I come through this edge 2 to 4, then it would be 4. No, 4 is the x is equal to 4 is the last definition before the call is being made. But if I come through this edge from x to x is equal to 4 to this x is equal to 3 and then call, right? Depending on the if condition here, maybe I am calling with x is equal to 3 happens first and then I call. So then the last def becomes this. So either this is the last def or that is the last def. Either of the two could be. And then I go, excuse me. And then I go, and the first uses also could be dependent. So it could be either, because this is the first use, right? Maybe this is the first use or maybe this is the first use, depending on the condition above. Maybe there's some if here. So if so and so, then z is equal to y, otherwise t equal to y. So what is your first use also differs depending on some other condition that might be there. Okay? It might be 11, it might be 12. So you pair with both. So you essentially get 2 11, 2 12, 3 11, 3 12. Okay, that's what you get. And similarly, the other side also we are mentioning it. No, we aren't. Okay, fine. So essentially, idea is the upshot is coupling DU path is from a last def to first use because that's what your DU pair is. So accordingly, construct path. Coverage criteria is same. Okay, all defs, all uses, all DU paths. Similar to what we discussed already within the same module, right? We discussed all that. The data flow graph was for one unit, no? So we already discussed that. So this is the same thing. Only the do pair changes the last step to first use, and accordingly you construct path because you can do that. No, we are just extending the same thing. Okay, so that's what. And there's some example. I'm not going to discuss that today. Fine. Yeah, this part is okay. Just remember the definitions and some key ideas from it. Okay. What is the specification? Yeah, so a specification, as you all understand, is like it is not code, okay? Because remember when we started software testing, we described that we are going to test artifacts. We did not say code, but predominantly it is going to be source code in general, program source code. But software is not only that, no, there are specifications also. There are other kinds of artifacts also apart from source code. Okay, so there are some specifications also, very important things that are there. No? Some model of the implementation, how it should behave. No, because we do designing and then only do implementation. Right? So that's what it is. So one popular thing is, I mean, there are other kinds of design specifications apart from this, right? But two things that are there important is sequencing constraint and state behavior. So this, with respect to this, we're going to see what it is. See, sequencing constraint is as the name says, sequencing constraints. What does it mean? It means what can happen, what can happen before and what can happen afterwards. So essentially order, right? Let's say if a file is not there, so think about it this way: only two operations are there: create file, delete file. Okay. Now if the file is not there, for example, I'm modeling it, some constraint I'm modeling. So assume if file is not there, I cannot delete it. Right? File has to be there, then only I can delete it. It means add file has to be called first before calling delete file. If there is no delete, if there is no add file called, then delete file cannot be there. And think about a queue. In queue, you have in queue and dequeue. If there is no person in the queue, how could you call dequeue? Queue is already empty. So in queue must be called first before calling dequeue, like that. So very simple example, but there are other complex constraints that can be modeled through this. Okay, some order. So sequencing constraints. What can happen first, and so on. In what order things should happen. Okay, so sequencing constraints are what differs between stack and queue. See, in queue it says first in, first out. So that's a sequencing constraint. I'm saying what goes in first should come out first. So that's a queue. But in stack it says last in, first out. So whatever goes on top comes out first. No. So that's what is the difference? Difference is it's between sequencing constraint only. No, between FIFO and LIFO. So that's why it is. So here's the queue example. Okay. So for example, as a precondition that is there. No, at least one element must be on the queue because otherwise the queue will fail. Similarly, in queue, some post condition that E is on the end of the queue. I mean, in between you cannot insert. Should be at the end, right? In the queue. So like this. So it says in queue must be called before. So how do I model this? This is like example, right? But there could be other such sequencing constraints. How do I model it? Okay. So there are some modeling techniques for this. Okay. Okay. So it says if there are no sequencing constraints, then some faults could arise, right? Because sometimes if the file does not exist, then I'm trying to delete something. No, it will throw errors and things like that. Right. So that's why it is important to take care. Like in this case, yeah. Open, close, and write. See, you cannot just start writing unless you open. Some sort of sequencing constraint is there, no? And if it is not open, then you cannot close like that. So what are natural sequencing constraints? I mean, we have to somehow infer it also at some if it is not explicitly given, that we understand that we open first and then we write, then we close. Okay. So that's what. Now there's some example constraints that there's an example constraint that is given. Okay. So it says openf must be executed before every write and so on and so forth. Okay. So you do the implementation like that. Now this goes something like this. Okay. So after the so we have CFG that makes use of these methods, and accordingly we test whether sequencing constraints are being fulfilled or not. Okay. Like are we violating constraints somewhere? Yeah. So for example, 1, 3, 4, 6 the path violates this. Okay. Let's see what happens. So 1, 3, 4, 6 is doing what? So it opens. 3 doesn't happen. Nothing happens. Now 4 I think is uh, writing and then closing here. 1, 3, 4. No, this is a different one. So okay, I think one opens it. 3 doesn't happen. Oh, okay. So perhaps there's a
There is
sequencing.
a
Go ahead, Indal, please.
there is a loop,
Mhm.
but there is a loop now from 3 to 5.
Yeah, but it mentions only about the path that it is violating some. It says check a path exists from node 6 to any of the nodes with right. Okay. The open app to close. I think what they are saying is if you have opened, no, then you must write before you close. I think that's what you're saying. They are saying. So in this case, what happens is I open it. Okay. I go to 3 and I did not write it. So this write is at 2 actually, not at 4. Okay. This is at 2. So I open it, I go to 3, nothing happens. I go to 4, nothing happens, and then I close it. So I'm not writing. So I opened it without and closed it without writing anything. Okay, so that is perhaps some constraint that we are violating here. Thing that is there. Yeah, this last one. See, it says a write T should be executed before every close. What it means? It means that if I have opened it, I must write. If I open and just close, then I violate this. So that's what 1346 is violating. At 1, I opened it, went to 3, went to 4, and then just close it without writing. No violation of constraint. Then if you're not willing to write, then why did you open it? That's what it is. You understand? And think about other cases where this could be problematic. Again, to an example, so might not convey the idea fully, but if you extrapolate, you understand what is going on. Okay, so these are some examples. Fine, just some example that is there. Now, state behavior is another thing. So this was sequencing. No, what should happen first and not like what is not allowed and before it and so on, like before and after. But not all sequencing constraints can be captured using simple constraints. Okay, some of them need the notion of a memory, right? Memory also is important, right? Because sequencing constraint is just saying before or after, right? First or last. But it might be that depending on current situation, your choice is different. You see, so you need some sort of a state also. You see, so for example, if the file that I am working on currently is having so and so permissions, then I am not allowed to write into it. But if the file that I am working on is having so and so permissions, then I should write it and then only close, like some other external thing that is there. So you need some memory to capture that. No? So that's what FSM is about. Finite state machines are useful to describe the state behavior in that case. Okay. So we need to maintain some count and things like that. So that's what we'll see in this one. And 4.5 is the last one that I'm going to discuss. After that, we'll take questions. And of course, we have to discuss that strongly connected thing also. So FSM basically it models the sequencing constraint, but in a better way. Okay. So how modifications should happen? Where I am currently, these are the two things, like the transition states and transitions. Okay. Now transitions can have guards or actions associated with them. So I'll show you a graph. See this. This is a very good example. Think of an elevator. Okay, elevator. So and I need to begin with some state. So I have to be somewhere. So this is the initial arrow, meaning I'm in the close. So the elevator's door is closed right now. Now assume that there is a button to open the door. Of course there is, right? I mean on the outside or within the elevator also you have one button. When you press it, the door is supposed to open. That's the action, right? So if the door is closed, if the elevator's door is closed, then if I click on that, so there's the trigger, right? Open button when it is pressed, then I make this transition. See, trigger is the act of taking that action, right? Make like whatever triggers that's this particular transition. Because there might be two outgoing edges, right? Open door or do something else, turn off light. So which trigger is being pressed accordingly, we switch to another state, right? Here only one transition is possible, opening the door from close. So trigger is this fine. Now there is a precondition. This is a guard. Okay, this is also known as guard. Guard or precondition are the same thing. It says elevator's speed should be 0. Then only I can make that transition. So what is the implication here? Implication is if the elevator is moving, even if the trigger is taken, if the trigger happens, I am not going to make that transition. So I will not move from close to open, even if I press the button, if the elevator speed is not 0. Say this is wonderfully captured in this small diagram. That is what it's saying. Okay. So precondition is the elevator should be stationary. If the elevator is moving, then even if I press, I will not move. So that is why it is a guard, right? Guards from uh, things that should not happen. Is that okay? That's why it is. And now once you press that button, so assume that elevator is actually stopped, and you press that button, so actually you will move to. So now your state will be open. Now if it is open, Then of course in this case, from open you can kind of come back to close also, but assume something where it's a one-sided thing, right? So once you, like for example, if it is closed, then you cannot close it again for that matter, right? So there is no edge from close to closed. If it's already closed, then you cannot go to again to the same state, or somewhere else. That's what. So this notion of capturing what can happen from where is nicely captured in FSM. Okay. So there are two. So these nodes are states, edges are transitions. Okay. And here it is just noted that what is the precondition, what is the trigger. So if open button state is pressed, then we should ideally open it only if the elevator speed is 0. If that is not the case, then I'm not going to make the transition. So this idea, this whole thing, very nicely captured in this, and I was able to explain it to you easily. No, so think about this. These are the design specifications. That's how we go about it. Now there's a notion of FSM accepting something. That's important because there might be questions on this. Okay. So idea is that you're going to start with the initial state, and the final state is again double circle, similar to how it is in CFG. In this case alone, for this particular FSM, it happens that the initial node is the same as the final node. It could be any other node also, and any other CFG, rather FSM it could be. The acceptance, the notion of accepting something is that you start from the initial node, and of course you have to start from there, and you take certain actions such that you end up at the final node. Okay. So then it is said to be that sequence is said to be accepted by that FSM, because again sequencing constraint, no. So what sequence of actions is, so I have a door, no, so I have open and close. So I cannot do close close close, or I cannot do open open open, but I can do open close. I can do that. No, that sequence is possible because I'm opening it then closing it, or on off, like that I can do if there's a light bulb or something, but I cannot do on and on repeatedly because it's already on, so I cannot do again. You understand what I'm trying to say? So that's what it is. So accepting means you start from some initial state and do a sequence of actions such that it is accepted. So in this particular case, and there are other variety of use cases through FSMs actually. In this case, so if I'm at S1, if I do 0, then I end up at S2. That's fine. But you have to, for it to accept, you must come back. On, not, I mean, in this case, come back, but finish at the final node, double circle essentially. So starting from S1, now if I give 0, I come to S2. So if I give 0, 0, then I finish. So 0, 0 is accepted. Okay. 0 1 1 0 is also accepted. So 0 is from 0 I go here, then 1 S3, then 1 again, so come back. So 0 1 1 and 0, right? So essentially, so what you have to do, you have to come up with some counter examples. Essentially what we could do is we could ask for some FSM will be given. So in the options you'll be having descriptions that it accepts the other thing, and so on and so forth. You have to select the correct option. What is accepted? What will this FSM accept? Okay. So accordingly, what you could do is you could create something which, so for example, it is the option is saying that if they are even, it will accept. So think about odd. So create an odd thing and see if it is accepting it. If it is not accepting, then it is the wrong answer, right? And so on. And think about it like that. Some small examples you do, and you'll be able to figure out what it will accept, what it will not accept, and so on. This is a 0 1 example, but other things could be there also. Okay. Is this okay? Any questions on this? The notion of acceptance is okay with everyone, right? I hope. Starting from the initial, going to the
Yes,
final.
got it.
Very good. Uh, okay. Now there is a thing that you need to be careful about, and it might seem like contradicting to each other, but it's important to understand this. Preconditions. We might say preconditions. We might say guard. We might say precondition, or we might say guard, and both are the same thing. Both are synonyms. In this case, at least the way we've defined it, I understand the English meaning sort of like contradicts, because if precondition is true, then the action takes place. If the guard is true, then possibly it is locking you from proceeding, right? But the way it is defined here is, if the precondition is true, then you take the transition, and if the guard is true, then you take the transition. So better to think in terms of guard allowing you to do that. If the guard is true, if the guard condition is true, then guard allows to proceed. Essentially think of it like this. So then this will be reconciled essentially. Okay. Precondition is true, you proceed. If the guard is true, you proceed. So therefore it says conditions that must be true for transitions to be taken, and therefore if you remember that elevator example, we had said precondition or guard, the elevator speed should be 0. Okay. I mean, if the elevator is not moving, then only I open the door. If it is moving, no matter how many times you press that button, it will not open. You see, that's what. We should not try that, however. But I'm just saying that is the ideal constraint that has to be put in. Okay, now yeah, triggering events is what happens. I mean, in the other, because there are variables that we are modeling. So what should happen such that you take that transition, right? Because precondition is okay, but to go from close to close, what I need to do? Open door is the transition itself. The act of opening the door being opened is the transition, because you're transitioning from close to open. So that is the process of transitioning. But what would initiate that? How would I initiate that transition? So this is the initiation. So that is the trigger, right? Because I press the button, then only I start that transition. And it might be that when you press a trigger, rather when a trigger happens in an FSM, multiple transitions could start to happen. Maybe. Okay. Maybe you move from this place to that place, and some other place, right? Ideally, at one time, I think hopefully we one transition only, but I'm just saying. Okay, so this is the transition itself, but this is the trigger by which this transition happens. Okay, so this is the triggering event and the change in variable, right? Because how do we model that? Again, some change, no? Because think of it like a button, right? So button is not pressed, so nothing happens. Now I click it, so the state of the button changes. No, button is now pressed. You see, you remember from JavaScript there used to be events, no? So on click, button clicked or pressed. So there's a difference between if you know keyboard events, the difference between key down and key up. So key down event is when just after you press it, right? So it triggers, like just pressing it. You're not even lifted your finger from, right? So that's just key down. Key up is after you press it, and after you lift it up, then only the triggering will happen, right? So it depends on which event it is. And there's a key press event, which is you go down first and then key does key up, and then only it takes place. So subtle differences between these events, and I just gave an example, but that is the idea. Some event it could be. So here it says the open button should be pressed. Earlier it was not pressed, now I'm pressing it. So earlier it was like normal, when I press it, so some pressure I applied onto it, right? And it got pressed. So now there is a change, right? Change in the state. So therefore I take an action. Okay. So some equivalency is there, because again FSM is a graph. Okay. So it says node coverage executes every state. Of course, nodes are states, right? So if you do node coverage on FSM, what will happen? You're going to go through every state, right? So state coverage and vice versa. Edge coverage is executing every transition. So you had one open door, you could be having other things, in the larger FSM, not only for elevator but for something else, right? And then you do this. So edge coverage is transition coverage. Edge pair is transition pair coverage, and so on. Okay, data flow coverage we are not going to discuss on FSM actually, because why? Because only preconditions are modeled. There could be other variables also, no, in that program, in that module, in that whatever method it may be. But we are modeling only what is required for this particular transition, right? In this case, so there are other variables we are not capturing. Now what happens, this precondition is immediately checked, no? When I press, so I'm at the closed state, I'm pressing that, so immediately it is checked, then only it will allow me to go forward. If it is zero, if it is not zero, then so immediately I check that if condition is implicit there. So immediately after defining, immediately I use it. So therefore there is no notion of data flow as such. I mean there is, but uh, we are not going to discuss that at least now. Yeah, FSFs typically only model a subset of the variables. Like there are other things, but we are only modeling whatever is required for that transition or for that FSM only. Okay. Yeah. Depths of variables and triggers are used immediately. You see, because immediately we check, are we allowed to move forward and so on. So transition edges have different guards and different edges. Uses are different. Okay. Fine. Yeah, software design specification is not model. This is like sequencing, more for sequencing constraints. Okay. And then you have to generate your own FSM depending on the specification. This is for specification, not for source code. Okay. Because source code is the implementation, but some specification is there. Accordingly, you create a FSM. Okay.
So can you share that FSM of Q?
Yeah, yeah. Ajay, I think you requested that earlier also, but it slipped
Yes,
my
yes.
mind. Yeah, sorry about that. I'll create this one and share. Okay, on Discord.
Okay.
Hmm. Not now, because we have other things to discuss, but I'll do that. Similarly, you make it and so on. So again, you have to remember. So for example, the queue is already pushed. Sorry, it's already full. So now from object comma object, so assume two capacity is two. So only two things could be there. So if an object and object is already there, then you cannot call in queue before dequeuing, right? So queue is full, then you cannot in queue other object or other person here. Let's say you have to DQ. So for example, if you DQ, maybe you go to here or here, and if you call DQ two times, you go here again. Remember, but these questions always refer to the code, because the way code is doing might be different in the way we are thinking it. This is just my thinking that sequencing constants is like that. I don't know, right? But the way code is doing, you have to think like that only. Meaning from the code, you figure out what are the transitions and accordingly make it. See here, DQ cannot happen if the size is zero. Because I'm throwing exception here, no? If size is zero, then DQ will not happen, right? And so on. So this is what I do, right? I take the modulo and move forward essentially. I increment the position in which the next person is getting added. And capacity is 2, I think. So modulo 2. So either you are at the index 0 or at 1. Okay. And I think from null and null, you can either go to object null or null object. I think you go here first. This state, I think you cannot reach it, no? Because it's FIFO. Oh, no, no, it is like this. So you have null and null. Person comes in, so it's like object and null. So the other slot is still empty. Right. Then I move forward. Okay. So this object, it moved forward to this. And then the other, one more object came in. So it's object come object like that. But anyway, think about from the code perspective. I'll do an FSM for this one and share. Okay. So again, so you have to remember which call, which method goes from where to where. For example, you cannot go from null state to object immediately. Not possible. Even if you call in queue. Because in queue at a time it will only in queue one object, no? According to the code. Cannot push two things together. So from here there is no edge to here directly. You understand? So accordingly in the FSM you have to do that. Similarly, if you want to go from this to object common null to this state, or for that matter from this to this null comma object to null null, what you have to do is you have to DQ, right? So the thing that is at the front will get DQ'd and we go back to this and so on. Okay, again we have to refer to the code. Okay, yeah, here it says state object changes to null object with the call to DQ. Yeah, because we're DQing. Huh? So I think this front one goes forward. I mean, in this case should have been A B, so we understand the order, but it's both object. Anyway, from which side is getting added, we don't know. Okay, all right. This is that. So this is the idea in graphs. We discussed in up till week 4 it was graph. Week 5 we started logic already. The previous session we discussed that. So that was a different model, different technique altogether. But graphs broadly cover this. Okay. In structural coverage you have CFG and CFG with depth changes. That is DFG, data flow graph. So that you could have for source code, of course. For source code, for structural, for source code you have CFG, DFG. For design you can have call graphs. You saw that, no, coupling DU pairs. Call graphs is a different kind of graph that is there for integration testing. And for data flow coverage also you could have it. And similarly, structural coverage also for FSM, you have sequencing constraints for FSM. For sequencing constraints, you have FSM essentially. For specifications, this is not for source code, for a specification. Okay. What should happen when? Things like that. And data flow coverage, similarly, you have for design, you have call graph and coupling diopers. Okay. All right. So this is like broadly what graphs cover. So with this we end. And the last thing I'm going to quickly discuss, I know we are slightly ahead of time, but good that if you stay, be good because this is being recorded also. So now we are coming to classical coverage criteria. This is a different topic altogether. Okay, not related to graph. Some classical coverage criteria which were there and got replaced by newer versions of it. And essentially, you can think about it like that. Some terminology is getting changed. Okay, traditional terminologies for code testing focus on coverage, similar to how our coverage criteria is. Lots of other we have seen in graphs and even in logic we have other such coverage criteria. Here in this case we are going to see some traditional ones. Okay, so control flow is okay. This we have seen. Right, these ones. Remember this. Okay, remember the what is what. Okay, so in code coverage you would have statement coverage, branch coverage, decision coverage, modified condition decision coverage, and path coverage. Path coverage we have seen, right? Cyclomatic complexity. Statement coverage is not coverage actually. Okay, we'll see that moving forward. Cyclomatic complexity is used. There's a numeric value essentially. I'll describe that. Used for basis path testing and structural testing. Data flow testing is data flow coverage. We saw that already. Decision to decision path is also one thing. DD path. I'll show that. This slight little bit of discussion regarding this. Okay. DD path. So node coverage is same as statement coverage, of course, because every basic block is there, no. So every statement is there. So assume that if you divide it, different nodes, and do node coverage, all statements are covered. Edge coverage is same as branch coverage. Why? Because the conditions are on the edges, no? So if you are doing edge coverage, every branch you reach the true, false, one branch, the other branch, so on. Okay. Prime path coverage is same as loop coverage. Why? Because remember, all simple paths are loops. Like loops are simple paths, right? So if you are extending it, all loops eventually will be covered. So if you do prime path coverage, every loop is covered. At least one iteration. It depends on how many iterations you want to do, but at least one iteration will be covered for all loops in the program. Okay. Decision coverage and MCDC will be covered when you do testing with logical predicates. That is week 5. Okay. So this is the older terminology for what we are going to discuss in week 5. Active class coverage and so on. Okay. So that is going to come later. Now, cyclomatic complexity is a metric. Okay. So it just, so you have the CFG. With the CFG, you could just give a numeric value to indicate, essentially. That's what it says. No, the structural complexity, like some kind of average, not an average, but you get the idea, right? Like how complex that particular CFG is, that particular control flow is. Okay, that's what cyclomatic complexity is, and there's a number, there's a formula for that. So remember this. Now, what happens is, remember this part. Okay, cyclomatic complexity equal to, cyclomatic complexity is actually another term for the number of linearly independent paths in the control flow graph. What does it mean, linearly independent path? We'll understand that also. Okay. So so similar to how you have prime paths, linearly independent paths is a different thing in the CFG again. Prime paths also coming from CFG, linearly independent paths also coming from CFG. Okay, so if you do testing for all linearly independent paths, like if you cover, like creating test cases, like these are TRs again, test requirements. No, all my linearly independent paths are TRs. I'm going to do test paths for that to cover that. No, once I do that, then that is known as basis path testing. See, basis path testing, this is testing each linearly independent path. Like if you follow that, if you tour all the linearly independent paths, then it is basis path testing. Anyway, so see, a very simple definition is given here. Linearly independent path is of execution is in a CFG of program is a path that does not contain other paths within it. Like it's a sort of like a unique linear path though. It's not containing loops or things like that. Okay. Okay. So it says series of statements with no branches in and out is a basic block. So a list of all linear, it's a linear. How do you put it? Uh, it's a linked list of basic blocks essentially. You see, like that, in and out here, connecting all the basic blocks without any branches and things like that. Like on one branch you do it, then you do it independently on the other branch. So therefore, that is linearly independent. You understand? Another way to remember linearly independent paths is that you could trace a linearly independent path without lifting your pen. Okay. So if, see, I have a CFG, I'm going through, like I'm tracing some path, then I need not lift my pen to capture the entire path. Okay. So just like in one go I can do this. So that is linear. Because if it is not linear, then you might have to switch the branch and kind of lift your pen and then do the other thing, right? So that's not linear. So every time you can create a different trace, in one stroke essentially, then that is what linearly independent path is. Because that's one linear path essentially. Okay. So anyway, so to count just there's a formula to directly count it. Okay. So count that, which is the cyclomatic complexity also. This is the formula. Okay. M E minus n plus 2p. Okay. What is E here? E is the number of edges. N is the number of nodes. Just a second, please. I'm getting something. Okay, fine. E is the number of edges. N is the number of nodes. Plus 2 is a constant. P is the number of connected components. Connected components, not strongly connected. Okay. So in our case, most of the programs that we're going to deal with, most of the CFGs, you can safely assume P equal to 1. Okay, because it will be connected, only connected. We are not talking about the strongly connected here. Okay, so not connected component would be like completely different from in the picture. You could have a completely separated out CFG, like two portions like that, but that's not the case, right? If it's a one CFG only, then it'll always be connected, right, in some way. So therefore P equal to 1 you can assume, and therefore the cyclomatic complexity formula is E minus n plus 2. Okay, so yeah, that's why it says for graphs which correspond to a single program or method without any other procedures or method, meaning you're not calling other things, other libraries, other classes, like you're discussing only one CFG. That is it. There's only one connected component, of course. So cyclomatic complexity in that case is, and we are going to give one CFG mostly. Okay, so we have this E minus n plus 2. Okay. Now other thing is other way to calculate it, but there is a slight bit of uh, caveat here. This is easy. Always follow that. I'll remember recommend you that you remember this and follow this only. But there another thing. If if there is only one entrance point, okay, because there could be multiple entrance points also, multiple initial nodes and multiple final nodes. But assume that you have only one entrance points in one entrance point in a CFG and one exit point. Then
Sir, I don't
hmm,
think multiple initial points are possible. Multiple final points are possible. If you see in the first slide, it is written multiple initial points are not possible, I think.
oh, is it mentioned that multiple initial points are not possible?
Yes, yes, in a slide it is mentioned. I can share that.
Okay, okay. It might be that we are taking it like that only. Ideally, is that generally speaking, if we were to generalize it, in certain cases, you can think of having multiple entrance points also, because remember, mm, see, if a program is running, right? If a program is running, so it runs from the main method. Fine, runs. Now assume at the same time it is listening to some port and having an API also. Just kind of making a case, okay? Now to interact with that program, some other external thing is calling or doing a message passing or something, no, some API call, so that when the call hits, no, for that other thing with respect to that other program, that is the entrance point to this program, you see, because that's what the call is. See, I'm calling RPC. So for me, I understand that for the program itself there's only one entry point. Basically when you run it, no, that's the actual main, that is public void string main like that. But yeah, that's where it is. But public static void main string arguments, that's the common signature in Java, no, that's the main point. But that's fine. But then you could have another program calling a program which is already running, or maybe a library, right? So for that, it becomes that becomes as an entry point, right? That also can happen in certain cases. That's why this one is given, okay? But I think we are simplifying it and assuming that in our CFGs mostly we'll have only one entrance point, okay? That's fine. It's okay. But maybe again, final node could be multiple, okay? So this thing, the other formula only works when you have one entry point and one exit point, and that is equal to the number of decision points. I'll come to that, plus one. And this is what you're going to see in software testing also, I think. Okay, decision point plus one. So I'll show you here. So this one, how many nodes are there? One, two, three, four, five, six, seven. Okay, seven. Uh, seven nodes are there. How many edges are there? Excluding the initial arrow. That is not an edge. Okay, edge is only this. So one, two, three, four, five, six, seven, eight. Okay. So the formula is e minus n plus two p. P, of course, everything is connected here. So p is equal to one. So 8 minus n plus 2 is 3. Okay, that's what you're getting. Now here you see one entry point only, because initial node is 1. Final node is also 1. So the number of the cyclomatic complexity equal to decision points plus 1. What is the decision point? Decision points are your if statements. Any kind of outgoing degree 2. Wherever outgoing degree is 2, that's your decision point. Okay, even more than 2 also. It's like switch case, you can have multiple. That's fine. So you have one decision point, that is node number 1 itself, the top one, and the middle one, the center one, essentially. That's also a decision point, right? Because two outgoing edges. So 1 2, so 2 decision point plus 1, so 3. See, with both formula you're getting the same answer. Okay, but I would encourage you to stick to this one, because you never know if the CFG is giving given in another notation. Maybe there are multiple final nodes, and if you don't want to draw it, because the CFG edges are given directly, as a set, you can directly count it and subtract it, the number of nodes from it, and then get the number. Okay, in that case, you don't know how many final nodes are there, and so on and so forth. So even in that case, it's difficult to figure out how many decision points are there in that case, right? But whatever is comfortable, maybe you stick to this. Okay, so e minus n plus 2, that's what it is. Okay, because this is like more general, there's no assumption on this. Fine. Okay. Yeah, there's also another way of doing it through externally collected component, but you get the same answer essentially. Okay, this I mean, we may demonstrate this one later, because I don't have an example for this. But essentially there are two ways. Okay, either you do it with this decision points plus one, given that one entry and one exit points are there, is there only, or this. Okay, and okay, fine. Now, so basic path testing is all linearly independent paths. Okay, like the cyclomatic complexity. So the number of paths that will be there is how much is the cyclomatic complexity, right? So three. So three paths will be there, and I mentioned to you that without lifting your pen, you can trace it. No, so think about it this way: I'm starting from the first one. Show you linearly independent paths. Okay, three of them. First linearly independent path is I'm starting from the first one, and I'm not going to lift my pen. Assume. Okay, and I'm going to the left. So here, from the left to the down. Now think about it this way: if I am at the center node, then to go anywhere else, right? I mean, if I go to the left, then to go to the right, I have to lift my pen. But that is not I'm not allowed to do that. So I go to the left and again to the left. So the left path is how many? So there's one. This is one path, right? So only going to the left. So first decision point left only. Second decision point left. So you have this. So one or and so on. I mean, this is not numbered. It should have been numbered. But you get one. That is one. The other path is only going to the right. Okay, only going to the right. So that will be your from here to here, meaning to the right, and then from the second one to the right also, and this one. So that is the one. And the third one is for the first one, you okay, but we get four here, no? Isn't it? Okay, so for the first decision point, maybe you go to the left. And for the second decision point, you go to the right. Okay, so you get trace this path, which is like cross cross this. And and the other one is this one. So for the first one right, and for the second one left. But for some reason, I'm getting two paths here. Ideally, should have been three only, because one path. Ideally, I think I am over counting. But idea is that basically you trace how many of our linear paths are there, meaning without lifting a pen, and that many you get it. Okay. Yeah. So that is like a heuristic method that I'm mentioning. Okay. You have the CFG drawn, you can check like that to get the actual path. But perhaps I'm
But
over counting. Mm.
there are four paths, in
Mm.
this graph actually.
There are such four such paths actually if we do this, because for the first decision point you have a choice here, no?
Two choices, and then for third decision point, or we say the middle one,
Middle
we
one,
have
yeah. Right, right, right.
It's two
No, so
things.
I'm missing out on something in that case. I think with regards to the tracing. By the way, the decision point plus one is fixed. Okay, so don't get confused with that. And also the e minus n plus two b. What I am mentioning with respect to linearly independent path regarding tracing, I think is not clicking. But I had verified that earlier also. I think in this case I'm kind of missing some point. That's why maybe some overlap or something. No, actually, what is happening is, see, if, even if there are four paths, no, so maybe say there's some redundant path that we can cut on, essentially. Maybe not the same. Okay, it might happen. But in this case, for some reason, I'm seeing that it could be unique also, right? Because if you come from this side and go to this side, then these are the two, and maybe then in that case, I need not do it. Okay, anyway, I'll have to number this and check this. This one I'll check. Okay, this one I'll check and let you know why is that. With regards to tracing, I mean, this is something that I came up with. It might not be very accurate, but I think ideally it should, because that's what it means. Okay. So, but I'll
The
give you that.
formula will give always correct answer, right?
Yeah, yeah, formula will always give the correct. But
Okay,
please stick to that for the assessments and exams. Okay. This was just an intuition behind that. How do you figure out linear? I mean, like if I want to trace out how many linearly independent paths are there, like this is just the count, right? Formula will give you the count, but how do I trace it? So that's why I thought that that's a good analogy, and it worked also for some graphs. But this is a counter example, I think. Uh, Apparently we're getting multiple this thing, but perhaps I'm not counting it correctly. I mean, there's some assumption that I'm missing here in that case, because one of those is guaranteed to go away. Meaning we're getting four, no, if we're just doing that tracing. So we are getting four that way. But I think not all four are basis paths, of course, because it's supposed to be three only. So I think we are over counting in that case one. So that one I'll check and let you know, okay, how to fix it. Anyway, that's a discussion for another day. It's not important. For the exam, you can stick to that. Okay. So no, yeah, CFG analyzed to find a set of linearly independent paths of execution. That's what I'm saying. So how do you find it? Okay, now test paths for such a TR can be the linearly independent path themselves or any test path that contain this path, meaning touring, the notion of touring. No? You have prime paths, you want to tour it, so you construct test path, right? Like that. Okay, fine. Okay, now decision to decision path, you have to understand a little bit about it. Uh, okay, so this one, there's a slight bit of detail to it. So, okay, decision to decision part I'll take in the next one. Is that okay? Because I mean, this itself will expand into multiple things, but I want to take something else. So, is that okay if we skip this for now? The next one we'll discuss.
Sure, sir.
Okay, during revision we'll do. And anyway, we have quite detailed discussion with respect to this. You can watch the older recordings also. Okay, idea is that there are some. I'll give you a brief essentially. See, there are some conditions. Okay, which it must fulfill. Okay, and that is considered a DD path essentially. Okay, so DD path could be that, and it satisfies one of the following conditions essentially. If it is a single vertex with integrity 0, so initial vertex always taken separately. So that is one DD path. Okay, that is already taken. Okay, now so what could happen is if there is only one path fulfilling the condition, then you consider it separately. Right, but it could be that one single path is satisfying both conditions. I mean multiple conditions. So I'll show you what I mean. What I mean is, for example, 3 and 4, right? So so if you look at condition number if you look at condition number 4, it says it consists of a single vertex. Okay, single vertex, meaning separate path with in degree and out degree as one, meaning both in degree and out degree as one. So so if you think about 3, so 3 in degree is 1, right? Because only one incoming edge and only one outgoing edge. So with respect to condition number 4, this is a DD path. So then why have we taken 3 comma 4? You understand? Because we could have as well taken 3, but we have taken 3 comma 4. Okay, so basically what we are saying is there's some sort of precedence here. Okay, if it becomes a chain, okay, then you combine it and make it into a chain, maximal chain. That's what we are saying. Okay, so because what is a chain again? So for that we have to explain the chain. Chain is initial terminal vertices are distinct. Okay, all the interior vertices have both in degree and out degree as one. So that becomes a chain. That is just a chain, not a maximal chain. Now maximal chain is a chain that is not part of any other chain. Okay, that is maximal. So all maximal chains are DD paths of length greater than or equal to 1. Because for 1, anyway you could take it out separately. Like 3 anyway was being taken because of this condition, no? Because of the fourth condition. In degree 1, out degree 1. So 3 we take it. But if it is becoming a chain of length greater than or equal to 1, uh, right? Greater than 1 essentially. So we combine it. So that becomes 3, 4. Why? Because you see, with respect to 3, 4, the 3 in degree 1 only and 4 also having in degree 1 and out degree. So this becomes like a chain, 3 and 4 both. Okay, because you can see it visually also, right? Like that. And similarly, okay, so why is 2 taken then? 2 is taken because out degree 2, right? This is condition number 3. So it says it consists of a single vertex with in degree greater than or equal to 2 or, so remember this, with respect to chain it is and, okay, both in degree and out degree. So therefore only you get a chain like a linked list essentially. Okay, but with respect to this decision vertex, it is or. So either in degree 2 or out degree 2. Okay, so in this case with 2 with respect to node number 2, essentially we are taking it because out degree is 2, right? So this becomes a decision vertex and therefore we are taking it like a DD path. 1 is because of the initial vertex, in degree 0. So we take it separately. And then 2. So 2 is for decision vertex. 3 and 4 is a chain, right? In degree 1, out degree 1, in degree 1, out degree 1. So 3, 4. And similarly, 5 is taken separately because of the fourth condition. Consists of a single vertex with in degree 1 and out degree as well. Okay. Because 2 is already taken. 2 is already taken because of the decision vertex. Again, precedence here. Okay. And then so 5 is left alone. So because in degree is 1, out degree is 1, so you take it separately. And there's no chain here. In this case, 3 and 4 becoming a chain. But 5 is not becoming a chain, it's separate. A single vertex, so we take it. And final vertex again is taken because of this single vertex out degree 0. So that is terminal. So initial always taken separately, final is always taken separately. Decision vertices are taken always separately. And if it is a single vertex alone, like in the case of 5, you take it. But if it becomes a chain, then you take the chain. So only precedence with respect to this. If something is becoming a chain, then you check that take the chain and not consider separately. Even though I could have done 3 separately and 4 separately because of this condition, right? Both of them are individually satisfying this condition in degree 1 or degree 1, but it is part of the chain, right? So maximal chain, therefore. So therefore I combine it. Okay.
Can you
That's
tell the precedence order? Because I think the first and the second point we have to consider them at first, because 5, 6 could have been also a change in that case. So we have to consider the first point at the beginning. So what is the precedence of all these points?
no,
Could you tell?
no. 5, 6 could not be. Yeah, I understand what you're asking. So with respect to 5, 6, I'll tell you because that's what the distinction is, right? 3, 4 are there, but 5, 6 are not there. So actually, you see, with respect to maximal chain, no, not maximal. But to go back to chain first. See, chain is all the interior vertices have both in degree and out degree as well. Both. So 5, 6 problem is it cannot be
Oh,
considered
6
chain
has no
because
out degree. Yes,
6
got it.
is having no out degree. No, I
Yes,
mean,
yes, got
you
it.
understand? Yeah. That's why. So again, and 6 anyway taken as a final. So 5 you take it as with respect to single this thing, single vertex. Okay.
Only the last 2 points has the precedence. Otherwise, everything is.
Yeah, everything I think you can club it. It's fine. Sometimes it creates ambiguity. We'll try to make questions like that. It is not ambiguous. In case I'm just saying, in case multiple possible answers are there and that causes the discrepancy, just alert us like after the assessment, and we will take care of that. Ideally, it should not happen, but we take good care that
Yes.
avoid that. But maybe sometimes it may happen, right? Because the precedence order is not explicitly given, but that's what I make out from this essentially, that with respect to this only you have to be careful. With regards to the other ones is fairly clear. Okay. Because initial
Okay.
vertex, no other thing could be initial vertex anyway, right? Because so you consider it separately, you have to. Similarly this one and similarly this one, single vertex only. So every decision vertex you take it. Only with respect to chain, either you combine it or not combine it. Okay. So if you can combine, like if it becomes a maximal chain of greater than one, then you do that. If it does not, then you don't do that. Okay. So so that's what it is. I mean,
Okay, sir.
in some sense, with respect to 5, it is following both 3 and 4, like both conditions, no? 4 and 5. Because 5 is also because it's a single vertex in degree 1 and out degree 1. Also is a maximal chain because there's no other. I mean, we cannot maximize it. We cannot extend 5 further. So because it says equal to, doesn't take greater than, strictly greater than, so equal to also. So
Yes.
it falls in both essentially, right? Because both, but anyway, both are single. So in this case, fine. Only thing is, if it becomes greater than one, then you take that one, similar to the case with 3, 4. Okay. If it becomes greater, then you take the greater. Fine. Okay, fine. So we've come a long way. Thank you all for being here for so long. Now, the last thing that I'm going to discuss with respect to a strongly connected component, which I think Arjaya had asked about. I'll just give you an intuition behind the algorithm. Even Kosa Raju's algorithm, the key idea is same. I try to write it on Discord. I understand that unless you see a graph and it being done on it, it's difficult to figure out what is happening. So I'll show you quickly. Actually, I've taken a graph, and what I have done is I've taken a fairly simple graph and created a graph and its transpose. So both are already with me. So what I'll do is I'll do a run through of DFS by hand and show you how the algorithm works. What is the essence of that? How do we get the strongly connected components? Just a second. Let me share with the other screen also. Yeah, before that, any questions? Otherwise, after the strongly connected discussion, we may as well wind up for today. So before that, any questions are there from anyone? If there are, then we
So
can
for
discuss.
quiz,
Hmm.
one the syllabus is from week 1 to 5, 1 to 4, right? The 5 is not.
1 to 4, 1 to 4, yeah, 1 to 4. 5 is not there. 5 is not there. And with respect to the revision session, that is going to be on Thursday. Tuesday again we can discuss things. Okay, with respect to the exam also, it's completely fine. But we will do some course like content discussion also. So it might not always be uh, with respect to only revision, but a dedicated revision session only with respect to quiz one, like only week 1 to 4. We are not going to discuss anything else. That is scheduled on because content is somewhat dense, right? So you have to have multiple sessions to cover the entirety of it. So 12th, on 12th, that is one. And one thing I just like to tell you also is that I'm also planning to, because we regularly do that essentially. So 12th is like the revision session. We are going to discuss the concepts and solve some questions. Also, we'll try that. And also either on okay, there's only one day after that. So most likely on Saturday. I'm not sure. So if you want, like we'll be in the office hour session again. So for the last minute doubts or some problem solving, maybe some old papers, some ambiguities there, something like that. No, because you may be solving the quiz papers also. So earlier papers, some corrections might have been there, something like that. If there is, then we can discuss that also. Okay, like and quickly solve it also. So we'll see if that is possible. But 12th we'll have the revision session. Okay, so that is the agenda. Now let me go forward with this thing. Just a second. Let me share this. Hopefully the pencil works perfectly this time. Uh, Apparently some issue with the pencil that I'm using, so it gets stuck sometime. Okay, so let's see. Join from here. Got a graph. Just a second. Let me. SCC. Yeah, this one. Both G and GT. Okay, so let me know if the screen is visible. Not this one, the other one. Just a second. Is the screen visible? The graph?
No, the Excel sheet is open.
Excel sheet, okay. See, should now be visible. I think I have to stop sharing. Is it visible now?
Yes, sir.
I think both are visible. Just a second. Let me stop sharing here. Okay, visible now. Fine. So see, this is the situation. Okay, I have G, and I marked one strongly connected component, but you can. I mean, there is only one in this case, but you can extend this idea to other. Ideally, we should have one more, but anyway, I mean, I'll try if I can extend this also. In this case, only one. So the difference between G and GT is that it's G is the graph and GT is the transpose of it. What happens with the transpose? Transpose is just flip the edge, every edge. So 1 to 2 was an edge, right? So here we have 2 to 1. Okay, that's what happens. Now the way algorithm works is, one thing you have to just immediately notice is that if you have a graph, then if you take the transpose, then whatever is strongly connected will remain strongly connected, even though the graphs, the edges are switched. So for example, 2, 3, 4, or 2, 4, 3 for that matter, or 3, 2, 4, 3, essentially this one. 3, 2, 4, 3 is a strongly connected component, of course, right? But even if I do that in the red one, in the GT, the transpose, even in the transpose, I have 3, 4, 2, 3. It's the same thing, right? So I have the same component in both the graphs, even after. So that is the first key insight on based on which these algorithms are working. Okay. Now what they do is they start DFS from some, some point. Excuse me. So that's what I do. So I'm doing DFS on excuse me. I'm going to do DFS on G, and as and when I finish it, okay. So we have to remember the finish time and accordingly proceed. Okay. So what I'll do is I'll use a stack. So as and when I finish, as and when I reach, I will keep adding the nodes there, like the visited node. Okay, I'll keep adding it in there in the stack. So because that is going to be helpful. So what we are doing is we are starting from one. So remember what is happening. How do I put it? So let's say there's a stack here. Just a second. No, not like this. Okay. I mean, you just okay. What I'll do is I'll write from basically what goes in last will come out first. So that is the idea essentially. Okay, but I'll try to write that down. Okay. Mm. This is just to keep track of the finish time. I mean, the exact number is not required. Only the order we want. So a stack is useful for that. We need not do this. We just remember that. Okay. We do it the other order. Okay, so assume that I'm starting from 1. Okay, so from 1 I could, the choice is mine, I could continue DFS in any way. So first thing I visit is 1. Okay, so I'll just write that down here. I'm doing on G. Okay, so 1. Oops. Sorry about this, there's some issue in there. Okay, let me see. Okay, so we do 1, and then from 1 DFS goes to 2, assume. 3 also I could go, but I'm going to 2, fine. And then I'm going to do, oops. Okay, unless I am able to write it clearly, it's difficult, no? Okay, so I got to do, and then from 2 assume that I could go to 5 also, no, there is no problem in that, right? So but assume I go to 4. Okay, because all these are unvisited vertices. I'm keeping track of. I remember you have to only write those which are which we are visiting for the first time, which already visited we are not going to visit that again. Okay, so from, let's say, from 4, uh okay, so from 4 I am from 2 I'm going to 4, and then from 4 I'm going to 3. Okay, this is all first time, and from 3 I could go to 2, but it is already visited, right? So now remember how DFS works, right? We keep drilling down, and now we are backtracking, right? Because from 3 I go to 2, 2 is already visited, so I'm not going to do anything. I come back to 3. Is there anything from 3 now? Nothing. So I then go back. So I go to 4, right? From where I came, I go to 4, and I see, is there something in 4? Other thing which I can visit? So there is nothing. I mean, there is 5. Okay, so there is 5. I come back to 4, and then I go to 5. Let's say this is the order, right? So I come back to 4 again, and then I go to 5 from here. From 5, again, I can go to 6 alone, right? So once I visit 6, there is nothing. So I come back, because from 6 there is nothing, and from 5 also there is nothing. So I come back to 4. 4 is also finished. So then I go back to the previous one, which is 2. 2 also, yeah, from 2 I can go to visit 5, but 5 is already visited, so I don't do anything, right? And from 2, then again, any other thing is there? No, 5 alone is there, but 5 is already visited through 4, so it's fine. Now I come back to 1, and is there anything from 1? Yes, there is 3, because remember we went from 1 to 2, so 3 is still there, but 3 is already visited, so I don't do anything. Now DFS is finished. Okay, so this is the order in which the nodes are visited: 1, 2, 4, 3, 5, 6. Okay, now, so I think everything is covered, right? 1, 2, 3, 4, 5, 6. Yeah, everything is there. So this is the DFS one traversal, DFS traversal of this graph. Now I'm going to take GT, which is the transpose of this graph. Okay, and I'm going to do a DFS. Okay, on this starting from the last node first. Okay, whatever I finished on, because that's what I do, right? Just
Okay.
a second.
Okay.
So yeah, so I go to 6, and then I go to 4, and yes, so I go to from 6 to 5, and then from 6 I'll go to 5. Okay, just a second please. So from 6 I go to 2. No, I'm missing out on something. Just a second please. Just a second, let me look into it. The order, I think I'm not doing it correctly. Just a second. This is fine. We do DFS first, and then reverse it. Hmm. Okay, so yeah, So it goes to 7. Oh, okay. Okay. Sorry. Sorry. I did one mistake here. Actually, we are only going to add to the stack when we finish. So I actually added immediately after visiting, but that's not the way. Okay.
Yes. After exploding.
Yes. Yes. Once it is finished, then only we put, because finish time, right? Okay, we are noting the finish time here. So that's what. So we are starting again from 1. Okay. So 1 to 2, we are not yet adding it, not like visited. Rather, we finish once we finish. So from 1 to 2, then to 5, let's say, and then to 6. Okay. And from 6, so I'm doing this way: 1 2 5 6. So from 6, then I cannot go anywhere else, right? I mean, at that I go to a dead end, so then I push 6. That's what the idea is. Okay, so I push 6 first. Okay, then I come back to 5 because 6 is already finished. I come back to 5. Is there anything else from 5? No, right? I mean, I cannot go out except 6 is already visited. So 5 is finished now, like nothing is there from 5. Now I come back to 2, right? That was the one. So 2, again there is one more thing, 4 from 2. So 4 is 2 is not finished yet. So then I go to 4 and then to let's say, so from 4 then you have 5, but 5 is already there. So then you go to 3. Okay. So and then from 3 you have 2 again, right? So and from 2, yeah, and so yeah, from 2 then you cannot go anywhere else, because what I did is from 2 I went to 4 and then to 3 and then back to 2, but from then 2 you cannot go anywhere else. So in some sense here 2 is finished, right? Yeah, because that's the last one.
Yes.
Yes. So I'm true, you cannot go. So now I'm coming back to 3, and this is the earlier 2 that was there, right? So I'm now coming back to 3. 3 is finished also, because only place I could go is 2, and 2 I already visited. Now from 3 I cannot go anywhere else, so 3 is finished. So 3. Now I'm coming back to 4, right? Yes. Now from 4, 5 is already visited, and 3 alone I could go. 3 is visited now. So 4 is finished. Now from 4 I cannot go anywhere else. So 4 is finished. Right. Now 4 is done. Now I'm coming back to 2, because from 2 I came in here, right? So 2. 2 is already visited. Is there anything else where I could go from 2? 4 is covered, 5 is covered, and that's it. Only 2 outgoing edges from 2, right? So that is covered. So 2 is, but 2 is already added in the stack. Fine. Now mm, that's it. So I come back to 1. Is there anything else that I could go to from 1? I could go to 3, but 3 is already visited. So now nothing else from 1. So 1 is finished. Is that okay?
Yes.
This is the order. Now you take the transpose. Okay. And so we are adding from this side. So last in is from this side. Okay. So this will. Right, right. Yeah, we are correct only. Fine. Because one's supposed to be an independent one, right? Because there's no strongly connected. Yeah, there's only one. Fine, fine. So idea is that we are going to figure out that, because other than other than 2 3 4, everything else is separate. So that's why. So anyway, now you take the transpose. Now you're going to start from 1, DFS from 1. Okay, the last thing, because we are adding in this order. So we are going to pop out in this order. Okay, so we are popping out in this order because we added this. So again, we are taking the transpose. Now on the transpose, we are going to do DFS from this side. So start from 1 now. That's what. So if you start from 1, you cannot go anywhere, right? From 1. So 1 is already finished. Like, I mean, there's only one thing, 1. So you cannot go anywhere. So 1 is done and that is finished. So this is 1. So every time you finish, no, that is the key point. Now every time you finish this DFS on the transpose, that becomes one strongly connected component in the original one. So this is the strongly connected component. This is 1. 1. Okay, now I'm going to 4. Next thing is 4, right? So I'm going to start afresh. DFS again. So from 4, I could see, that's the key part. Whatever was strongly connected remained strongly connected in GT, right? So therefore, if I start from 2, I could go to 3, I could go to 2, I could go to 3, and I could go to 4, right?
Yes.
So therefore, that remains whatever is whatever is in this DFS tree becomes a strongly connected component. So whatever I visited here, this is a strongly connected component, because I started from 4, so 4 to 2 to 3. and that's it, I think. Yeah, 4 to 2 to 3, and then from 3 you cannot go anywhere, so you come back to 2. Now again from 2 you cannot go anywhere, so you come back to 4. Now from 4 you cannot go anywhere, right? So 2 3 4 is already taken. So then you don't go back, right? So 2 anyway. So 3, 1 is already taken care of. Yeah, 2, you cannot do anything else. Fine. 5. Now you go to 5. Fine. So because the DFS finished, right? Idea is, see in the GT when you are doing the DFS, no, whenever it finishes like completely, that is one strongly connected. It in a strongly connected component. It has to be. That is the key idea, and you can see it here also. Right. One finished. So we got one strongly connected component. Now
So
two,
we are
three, four.
doing
Hmm.
so we are doing it like this. First we are doing the DFS for one, then
Hmm.
from that
Stack.
from the stack at the end, so it
Hmm.
comes four. So we are starting the DFS again from four.
Four
Okay,
from 4. Yeah, yeah, yeah.
like
And
that
whenever
way.
it finishes, like the complete exploration is completed fully, from that, like you hit a dead end essentially. Not dead end, but you get the idea. Like the complete search is finished. So that whatever comes in that node, no, that is a strongly connected component. So 2 3 4 comes.
Okay.
1 comes. And again, so what else? 5. So we start from 5 now. So we start from 5. We see that yeah. So we start from 5. Now 5 is interesting because from 5 I could go to 2, right? That's fine. And from 2 I could go to 1, right?
Yes.
But from 1 then I cannot go anywhere.
Yes.
So that's it. uh, from 5 to 2 to 1, and then from 1 I cannot go anywhere, so I come back to 2. Fine. No, but I'm just thinking about this case. So ideally what should happen is you're not supposed to go back uh, to the other one. Ideally you should get logged in essentially. See what is happening is this 5, you're going back to the same connected thing again, which should not ideally happen, but let's see. So you get to 1, and so okay, 1 ends. Assume that 1 finishes here. Now I'm coming back to 2. Fine. But everything that comes in the DFS is one strongly connected component, but this is not the case, right? So 2, and then I'm coming back to 5. Okay, let's see. So here I come back to 2, then go to 3, and 4. No, I think in the order in which we added, no, this one is slight problem there. Because we went in there, then to 6. 6 got finished, we come back. 5 got finished, we come back to 2. Yeah, this is correct only. Why is it that we are coming back to this? Just a second. So, okay. The end of each successful DFS, we are having that. No? Yeah. So we finish it with respect to 5. Mm, 1 I hit a dead end. Then I come back. Okay. I mean, so 5 to 6 certainly we cannot go. So I see if you do for 6, then again 6
Oh,
becomes, yeah, that is okay. Only with respect to 5 I am having a little bit of confusion. So you have this. If I'm coming back, then DFS ends there because it will succeed. So whatever it includes has to be part of this. So you do it from 7. 7 is alone. That's fine. I'm having another example here. Mm, Okay. Oh, okay. So you're going to start from there. Okay, fine. I'm not sure what happens with respect to 5. 4 I started. So yes. We do the steps same. Okay. Oh, okay, okay. Sorry. So one key point I missed here in the algorithm. Actually, we are going to skip those things which are already given in the previous step. Okay. So therefore,
Okay,
from 5, we are not going to go back to 2. That's what.
okay, okay,
Yeah, that is the. Because I was considering going from 5 to 2 again, but that is not allowed. Actually.
okay, got it.
Okay. So that is the. Yeah. Once we do that, then it is resolved. So from 5, you cannot go back to this one anyway. 6 you cannot go, and 4 also you cannot go. So 5 alone remains. Fine. You're going to escape on that essentially. That is
Okay.
fine. Okay.
So
Whatever is. Hmm.
when we are doing from that reverse, so are these the crossages from 1 to from 4 or 2 to 5? Are these
Yeah,
crossages?
these will be in the DFS, but I have not made a tree. If I made a DFS tree, then you see that this will be cross edges. Like if you want to join them, that'll become a cross edge. Okay,
Okay,
and similarly 6. So that key point that I was missing is that you cannot you're not supposed to go back to whatever is already taken. Why we did for 234 is 234 was not taken. That is the key part. 234
yes,
when we were doing that, no, none of the nodes in the strongly connected component were already seen. So therefore we could not skip it and we had to traverse. When we traversed, it became part of the part of one SCC. Okay, that's what.
yes, yes.
So that is what the idea is. Essentially, we are locking it because remember intuitively also that assume that I have a situation like this. Okay, having node here, node here, node here. This is strongly connected. Now this is going there, and I'm having a node here, node here, node here, node here, like this. Okay, now this is this side. So if I do DFS from here, right now from this side, now assume from this side I'm doing DFS. Okay, now it comes because it can come from this side to that side. Fine. Now it can touch upon certain things. Fine. And again, also you'll take this and this. Fine. So this is fine. One DFS will do that. So it's fine. Whatever comes. Now I'm having order. Okay. Now I switch it. So this part cannot go from this side to this side. That is the intuition behind it. Now I switched it this side. Become this side, but whatever was strongly connected remained strongly connected, right? So if I start from this side, I'll be logged in this strongly connected component. Like again, if I start from DFS from this side, because I cannot go like, but this remained strongly connected, remained strongly connected, but whatever was not strongly connected, it got flipped essentially. So I cannot reach the other portion, right? So if I do DFS, I'll reach this. Similarly, again, so this becomes a cross edge now. So this side I'll have to start again, and I do this, I'll get another. Okay, because the bridge essentially you flipped it, no? So you cannot, you're logged in, and that's why the order matters. Okay, so you have to start from
Okay, sir.
one then. Yeah, same thing happened here. Actually, we went on to 5 from here, right? But then 5 got flipped up. So and since we logged in this strongly connected in GT 234, from 5 we cannot go back to 2 again, right? So that's why. So in some sense, by flipping the direction, we are locking the DFS within the same strongly connected component. That is the key idea. So every time it finishes, we are sure it is a strongly connected component. Okay. Okay. Is that okay? Make sense? Hope it
Yes,
was
yes, I
helpful.
got it.
Yeah. Got it, right? Okay. Thanks.
Yes.
Okay. So anything else? Otherwise, we'll wind up. Thanks for being here. If there is nothing else. So in some sense, the DFS, if you're doing it in a stack, no, whatever the node is with which we started will come at the end. And in the reverse graph, we have to start with the one with which we started in the original graph in some sense, right? I mean, that's
Yes.
what it is. Because the stack, this is what is happening. Because we started in G with 1, and GT also is starting with 1 only, right? With this side. And whatever we finished of, you know, Next.
So once we get a strongly connected component, we will disconnect all the edges from that part, right?
Yeah,
And
yeah,
then
that's what.
again, okay.
Hmm. That's what. And that is happening only because of the inherent nature of a strongly connected component, that when you transfer, it remains connected. Had that been the case, that you do a transfer,
Yes.
then that not like it becomes a disconnected component, then that's a problematic thing. You cannot do it. This is only because of that. What remains
Okay.
strongly connected, I mean, what is strongly connected remains strongly connected. And other things are not connected now, you disconnect it. So therefore
Yes. Yes.
this lock works essentially. So you lock it in the same part, and therefore take it. Okay. But the key part that I was also missing with respect to this one is, once something becomes part of one strongly connected component, then you are not allowed to traverse. Like from 5 to 2, you are not allowed to go. Okay, because already taken in GT. Okay, all right. So that is what the slide is saying also. Now, if you go back and check and do it on your own also, you'll be able to get a better idea. Okay, so in this case, I think 5 also becomes a separate components. I have how many? One, two, three, four separate strongly connected components, because individual nodes we also take it. So four of them. Okay, we close. Thank you. I'll share the recording once it is available on the space. See if we
Okay.
can put it on YouTube also. Some discussion with respect to week 4 at least, if that can go. Okay, thanks.